You have stuff for me. Chapter 2, Section 1. I'll come around, please. Make sure your name's on all that fun stuff. Okay. I want to remind you all, here in the web links section is the web links for the playlist for the videos, which are all here in chronological order. If we go to this playlist here, there they are in order. Thank you. Additionally, at the bottom of our Canvas page are the physical uploads for my handwritten notes that were under the camera. So there's a Monday stuff down there at the bottom. Those will also be in chronological order. Today, I want to talk about something we've mentioned in passing, the idea of propositional equivalence. Do two propositions generate the same truth table in all cases? We did examine this, talking about converse and inverse and contrapositive of a conditional statement. We wrote through all of the truth options to see what was going on. Propositions that are logically equivalent allow us to do simplifications and make our lives easier. And we had a definition. I am up on this little bump and it is causing my handwriting to bug. A proposition, a compound proposition that is always false, regardless of the truth values of its component propositional variables. So I don't care whether P is true or false, Q is true or false, or any of the other letters individually represent something true or false. If the overall result is always false, we call this a contradiction. I'm going to change one word. If I change false to true, we're going to call this a tautology. And something that's neither always true nor always false is called a contingent statement. Or a contingency. The truth value is contingent on the individual variables. But if whatever truths or falses I put into the variables doesn't matter, and I get the same overarching result out of the whole thing, that gives me either a contradiction or a tautology. An example. regardless of whether or not P is true or false. What happens here? Well, yes, but then I do the or, so what happens? I'm going to get true out of this. Because if I have P, it can either be true or false. The negation is the opposite of that, but then I OR those together. And this is the inclusive OR, but it doesn't really matter in this case. What's the result here? Regardless of what I'm doing, at least one of these is a true statement. There we go. On the other hand, what happens here? Evan?
They're both going to be false.
Exactly, because this is an and now. And is only true when both are true at the same time. That's a contradiction. Questions? Yes, ma'am. Sure. It just will require me to have more than one variable involved. Any of our base truth tables from the other day are contingencies, right? If I do P and Q, then I have this. And so that resulting column has both truths and falses floating around in it at the same time, and it depends on the truth value of the individual pieces to tell me which output I'm going to get. Other questions? Percy. We had the idea that these propositions would be equivalent if they generated the same values. If this gave me the same result as some other combination of P's and Q's, those would be equivalent. One of our base operations told me when the truth values matched. Which operation was that? Chris?
If Q then P and then not P, then not P.
Those were two things that were equivalent. So that was an example. But if I back up further and I just look at the operations themselves, and or if and only if, not all of them, there was one that said, hey, when these match, I'm going to give you a true. Colin? It was my if and only if. So I can think of a tautology as the result of, hey, these things match, which is what you were giving me, Chris. P, if P, then Q. If not Q, then not P. Those had matching columns, right? What I could say is the phrase, if P, then Q, is logically equivalent to the phrase, if not Q, then not P, right? Notice there's nothing mentioned about a tautology here, is there? So why did I introduce this idea of a tautology now? Because another way to show that two things are logically equivalent is to create an if and only if statement. This logical equivalence means that this is a tautology. So a way to look at my idea of being logically equivalent is to say, oh, thing one is equivalent to thing two if I set up the if and only if thing, and I get a tautology. I would like to know if these two propositional expressions are equivalent. The answer will be yes. This happens to be a well-known rule. This is one of De Morgan's laws. But if I want to know whether or not this is an equivalence, I think the way to do it is to look at one sentence, and that is the sentence composed of the if and only if statement, not P and not Q, if and only if, not the quantity P or Q. I want to know if you build a truth table for this thing, do you get a tautology or not? Fortunately for me, there are only 4 rows in this truth table. There are a lot of columns, but there are only 4 rows. So let's do this. There's my starting setup. You have to decide how you are going to build this if and only if statement. We could build the thing on the left parentheses here, and then build the thing on the right, and then do the if and only if. We could do it in the other order. We could build the thing on the right first, and then build the thing on the left, and then do the if and only if. It's up to you. But the order in which you do this will tell me which columns you need where. So, how do you want to proceed in building one of the pieces of this expression? So we're going to do the thing on the left? Okay. If I'm going to do the thing on the left, I need not P, I need not Q. And the thing on the left ands those together. Yes? So, and those. What do we get? Beethoven. What do I get? Exactly. Thus Beethoven. Da, 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 da. 3 the same and 1 different. Not P and not Q. I have to put the header on the column or I will forget what I wrote. Okay, that's my left-hand side. Now, because I know that's my left-hand side, I'm going to call it that LHS for left-hand side. So I remember that's the left-hand side of the if and only if. I need the right-hand side. To build the right-hand side, I don't need any of that because the right-hand side starts with P or Q. I need to go back to P and Q, the originals. So I need to go all the way back over here to these 2 columns and do P or Q. I don't have to cover them. I just think it's useful. Prevent me from going back to the wrong column on the left. So P or Q. What do I get here?
True, true, true.
Ah, true, 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 false. Because that's our inclusive OR. Now I need the negation of that. Hey, looking false, 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 true. This is the right-hand side. As a human being, I can compare one column to another. And I can say, oh, look, the left-hand column is the same as the right-hand column. These are propositionally equivalent. They generate the same truth tables everywhere. But left-hand side, if and only if right-hand side. Wait, I didn't have to write out the whole damn thing again. Ah, I'm comparing these two. What does if and only if give me here? Here. I get a tautology. Any single row that spits out a false, stop right there. You're done. Those are not logically equivalent. In the final column. Only applies to the if and only if column. Now, as I said, the other way to do it is to note this column matches this column. But if I were an algorithm, or if I were a computer or a robot, I'd be checking, oh, did I end up with a tautology or not? Because that's a yes-no decision. I don't have to do a matching set. Questions? What does this idea mean in English? Let's translate from geek speak back to English. A proposition. I need a P, I need a Q. So let's make up a sentence. What do you want to use for P and Q? Literally, I don't care. Let's give me something that we can talk about. That's an if then. So my laptop is dead. That's a true or false thing. You want to use it won't turn on as the other thing? Well, no, I want to look at what these pieces mean. So what does this sentence mean in terms of those things? If I say this, using P is my laptop is dead, Q is it won't turn on. What does this sentence mean? You'd use not in the original. So it will turn on. My laptop is not dead and it will turn on. What does that sentence mean? Without the not on it.
My laptop is dead or when it's been
My laptop is dead or it won't turn on. The negation of your sentence is your sentence. The opposite of my laptop is dead or it won't turn on is my laptop's not dead and it will turn on. I negate the pieces and I change the or to an and. Think of this like the distributive rule. I've got a not on the outside of the parentheses. I want to distribute. So I should put the not on each piece, right? But I have to change the operation in the middle to make it mean the same thing. If I said, My laptop is dead or it won't turn on. I said my laptop's not dead or it will turn on. It's possible one of those things is true and not the other, right? That's what an or still does. But in order to make it equivalent, I have to change that or to an and. So this is an interesting idea. I have to change not just the two pieces with the negation, I have to change the operation in the middle. So the way our equivalences work allows us to construct sentences in English that reflect more accurately what we want to see happening. Questions? I want you to do another one for me. I would like to know if this is a set of logically equivalent propositions. P and Q, the quantity, or R, compared to P and the quantity Q or R. Excuse me. I've got 3 propositional variables. How big's my truth table? I'm going to need 8 rows. Now, here's where another reason to look at the tautology comes into play. I was very pedantic, and I make my truth tables the same way every time. I make them P, Q, R, with the right one flipping back and forth each one. Then the next one flipping back and forth twice as often. And the next one to the left flipping back and forth twice as often. And that gives me all the options. If you wrote these in a different order, then your rows might not match my rows. Yes? But your if and only if statement doesn't care. I just need to know, did the last column have all truths or not? And that's an easier decision than trying to go through line by line by line, regardless of the order, to make sure I did everything the same. So, build. Are these equivalent? I'm going to work in the same setup we did before. I'm going to turn this into an if and only if. I'm going to build the left side. I'm going to build the right side. Now I'm going to do the if and only if between them. So I start with the left side, means I start with P and Q. When I do that, that is false everywhere except those top two. It's only true when both are true. It's an and. That's these two. Then I do that or R. P and Q or R. So now, I don't need those two columns, I just need these two. It's an or. Or is false when false when both are false. That's here, here, and here. At least one of them is true everywhere else. That's our left-hand side. Now I got to do the right side. Right side means I start with Q or R. I don't need P. And again, or is false when both are false. Now do the right-hand side. P and Q or R. What do you get? Yes, sir. Now, as a human being, I can compare the column that says LHS to the column that says RHS. As an algorithm, I should finish the if and only if. If any row in this column generates a false, I'm done, walk away. Those are the same. Those are the same. Those are the same. Those are the same. Bing, 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 bing. Stop. What does that mean?
The contingency.
It's a contingency, yes. But what does it mean for our propositional expressions up here? They are not equivalent. As much as I wrote, oh, are these equivalent? That's why there's a question mark there. The answer to that is now no. These are not equivalent. Now that means that if I say P and Q or R, notice how the emphasis verbally put P and Q together, that's this. If I say P and Q or R, that's the emphasis here. Those mean different things. Depending on what P, Q, and R represent, these could be very different sentences. Yes, sir.
So for the if and only ifs,
Yes.
do they almost kind of work like an and because you need to have both at the same?
But and only works when they're both true.
Oh,
If and only if works when they're both the same. It's the logical version of do they match? Now, in general, I could say, I want you to tell me if these two propositions are equivalent. Here's propositional expression 1, here's propositional expression 2, and you build a truth table. But every time I add another letter, I'm doubling the number of rows. If I give you 7 propositional variables, that's 128 rows. Really? I have better things to do with my time, and you do too. So I would instead say, what are equivalences that are known? So that I can look at a complicated expression and start to condense it to make my life easier. If rearranging the parentheses here had worked, then I'd talk about associative rules, because that's the way it works in arithmetic, right? On page 29, I got a big list. Now, in this list, the capital boldface T represents something that is true regardless. Capital boldface F represents something that's false regardless. So these things, when I use an, I'm back here. When I use an and with something that is true, the item that is true really doesn't matter, right? If I say P and this other thing, the other thing is always true. And only works when both are true, right, Ryan? So that's the same as just asking me, is P true or not? Or works as long as one of them is true. So if the other side of the or is a false, then I really only care about the left side. Is that true or false? I can remove those other two things. I can squish them down. Basically, those disappear and I get an identity. Or works the other way. If I have an or with something true, then I don't care what the other piece does, because or only requires one of them to be true. The right side is true. It dominates the other side. It doesn't care. Wipes it off. Same thing with a false and an and. Idempotence. Doing the same thing twice, right? P or P. Why'd you say it twice? Double negation. Commutative. Ands and ors are order independent. If then, not so much. But and or, I don't care what order you write the stuff in. Associative works. But what's different about the version that's up here than the one we just tried to do?
It's like and then or.
Those are all the same operation in there. The one we did had one and one or, and that's why I wasn't allowed to rearrange the parentheses. When they're all the same, I can group them however I want. When they're different, I have to pay attention to the order. Distributive rules. I can distribute across the parentheses. But when I distribute, I have to take not just the P, I have to take the operation with it. So this first one says P or QNR. It becomes P or Q and P or R. Like I moved this whole expression across the parentheses and I left the and in the middle. Switch them around, and the same thing applies. My buddy De Morgan. If I distribute just the negative, just the negation, I put it on each piece and I flip the sign in the middle. The negation of P or Q is not P and not Q. The negation of P and Q is not P or not Q. This is where the exclusive or idea comes from. Do you want coffee or tea? Yes. But you can have not coffee or not tea. Not coffee. It's an or, right? I mean, not should be an and. Absorption. An extra or an extra and on the outside gets wiped away with the other thing. This goes back to our domination idea, because the P is in two places here. These are the ones we did as our beginning, right? An idea of a tautology and a contradiction. I will never, ever memorize these. You shouldn't either. You should put a Post-it in your spot in the book here. If you have the physical book, put a piece of paper right here. If you have the ebook, put a bookmark on this page. You will get notes for the exam, right? That was the hint dropping of something that should be on your note sheet. Yes,
What page?
29. As a matter of fact, I like these, but you'll notice all of these only involved and or not. We had other options, right? We had if then, we had if and only if. There you go. One of the things I notice is the first piece in table 7. If P then Q gets rewritten without an arrow. In 2 different ways. Here it is with an arrow, here it is without. Wait a second. If you want to build circuits that are if-then circuits, you don't need a separate if-then sort of thing. You can build it out of not, and or. And on Monday's discussion, I had those little symbols, the triangle with the circle on it. That's the inverter. The and gate, the or gate, those are physically makeable out of silicon. I can physically put them on the surface of chips. I can do an if-then in chips because I can make it out of and or and not. Same thing with an if and only if by building it this way. It turns out, here's an even crazier idea. You can build all of these structures out of just one type of gate, the negation of the and. The construction is disgusting and ugly, and I'll leave it to your hardware design people if you're going into hardware engineering. Otherwise, the hell with it, just go buy the chip that has the right thing on it. I showed you the TI link to the web chip page. In my office, I was talking about that defibrillator cable. I burned out chips as I was building the actual item. You know, you put too much current through a piece of electronics, what happens? The mystical gray smoke escapes. That's what makes electronics work, the mystical gray smoke. When you short circuit something, the mystical gray smoke escapes and it doesn't work anymore. I burned out 4 different chips. I kept them. I put a chip in a chip holder and I bent the legs out and I stuck it and I put a little pair of wires on the top of it. It's an antenna. I have a computer bug. I made a physical bug. It sits on my counter. I kept them, my whole bug family for my debugging process. Finally got the thing to work. Do you know that term actually comes from a physical insect? Admiral Grace Hopper was the first programmer for the Electronic Numerical Integrator and Calculator, ENIAC. It was made, instead of with chips, it was made with tubes. Each tube had a transistor in it. And if the transistor was flipped one way, it was a 1. If it was flipped the other way, it was a 0. But she went to fix something because suddenly the program wasn't working, right? And she walked in and one of the tubes had been knocked over slightly, so it was disconnected at the bottom because there was a moth on it. Beating it, it had died in there and gotten caught in the electronics. She taped it into the logbook. It is the first example of a computer bug. I wish I was making this up. Admiral Hopper gave a talk here in the late 90s. You should have all of these at your disposal when working on this idea. Because if I want to sit down and look at some crazy propositional expression, here we go. This is disgusting. We're going to do it anyway. This is gross. I don't like it. It's nasty and unpleasant. And I think it would be much better if this was a simpler expression. Somebody hands me this and says, how do I know when it's on, when it's off? What truth values do I need? I could build the truth table for this. I don't want to do it. So let's not. Instead of building a truth table, let's take our equivalences and see what simplifying we can do here. And as I simplify and combine, maybe this will become an easier circuit to understand. Okay. My first reaction on looking at this is, ew. But I have a not outside a set of parentheses. There's an and in there, so let's distribute. That's our De Morgan idea. So if I use De Morgan, I distribute that to each of the pieces, and I change the sign in the middle. With me so far? I put the not on each of the things inside this first set of parentheses. And I flip the and to an or. What can I do with that? Oh, me being the jerk that I am. I want to write down why I did that. Do you remember geometry class? We had to write down a reason next to each thing. Basically doing that here, but that's me being a pain in the neck. Okay. Now I've got this thing. What can I do on this side that will make things nicer? Because this is two negatives, right? A double negative cancels each other out. That'll become a P. Great. So that's equivalent to P or not Q or, oh, hang on a second. P or Q. It is at this point that I notice I made a copy error. We have not dealt with anything that is with me for this copy error yet, but I'm going to go back and change something. That should be an and, not an or. I haven't done anything to deal with that yet, so I haven't screwed up. So far, so good. But now I look at this and I say, can I make this simpler? P or thing, P or thing. And there's an and in the middle. This is the distributed idea, right? I have the and across both the pieces. So let's factor it out. Let's undistribute. So forgot to write it down again. Double B-O-U-B-L-E negation. Now, P or, what's left behind if I use the distributive rule? Pull out the P or. What am I left with?
Q and Q.
Not Q and Q is? Which means the thing inside that parentheses is always false. Now, I have a P or a false. Way back at the very beginning of the list, I said when you have an or works when one of them works. So asking P or false, this one's never going to work, is it? It's always false. So really, I only care about whether or not P is true or false. In other words, the identity law makes this just a P. In other words, this crazy looking combination of things can be reduced to one switch. Is P on or off? All I need to know. Now, I will be the first person to tell you, I don't think this is simpler because I have to have all of these tables on both sides and be able to know which way I want to go. And for small numbers of expressions, a few variables and a few operations, this is more reasonable to me to make a truth table. But as these expressions get larger and larger and uglier, I believe it is more useful to do something like this. A lot of proof engines and logical, I don't want to say AI systems, but learning systems are designed to do this sort of verification. Things like GON and lean are aimed at reducing these to other propositions that we know. Later in February, the Math Association will be having a talk by a gentleman from CMU who gave a summer research program on using one of those proof engines. As soon as I get his abstract, I can give you all the information. I know roughly when it's going to be. It'll be closer to the end of February. But then y'all are welcome to come watch this talk. And I think it will be really interesting because it will address these ideas. Questions? A contingency is sometimes true, sometimes false, right? So a proposition or a set of propositions is satisfiable if it is not a contradiction. If there's at least one way of getting a true out. We talked about system specifications in Monday's discussion. That was a satisfiable idea because there was one set of flags that would give me a true at the end, right? If this is that setup, then I'm looking for satisfiability in a proposition by looking for a non-contradictory idea. And I mentioned Sudoku. A Sudoku is just a satisfiability proposition. Can you put all the numbers in the right places? This and this and this and this. 700 gazillion different ways to create a collection that works. A lot of logic puzzles and games work like this. There's a common game in anybody play chess? Okay. How's the queen move in chess? In a straight line, however it wants, right? If I give you an 8x8 chessboard and 8 queens, can you put them on the board so no queen can attack another queen? There are 8 rows and 8 columns in my chessboard. Can I put down 8 queens so no one can attack anyone else? Absolutely. But that means I have to have no 2 queens in the same row, no 2 queens in the same column, and no 2 queens on the same diagonal. Look at the and setup I made. 1 queen per row, 1 queen per column, 1 queen per diagonal. So there's a bunch of ands in there. And I could put a queen here or there or there. There are a lot of options here, aren't there? And I could write each of them as a giant collection of ands and or statements. When I have a lot of things I want to and together, instead of writing proposition 1 and proposition 2 and proposition 3 and proposition n, I'm going to steal from calculus. Do you remember when we wrote sums in calculus, that capital sigma? And we said, oh, I'm going to count from the first one to the last one. Instead of using a sigma, I'm going to use the and symbol in here. That represents the first one and the second one and the third one up until the last one. If you put in or, it means the same thing with ors throughout all of them. And a lot of our Queen's problems setups are written in that sort of notation. That's a loop within a loop right there on page 34. There are my Queen's problems conditions. By the way, there are 92 different ways on a chessboard to put all 8 queens so none can attack the other. If I make the chessboard larger, a 10 by 10 chessboard, and then give you 10 queens, how many ways? If I get up to 16, it is possible to do this in 14 million different ways. There are hundreds of uses here. By the way, De Morgan's law applies here. If I put a knot outside this whole thing, I move the knot to the inside. But what happens to my and? It flips over and becomes an or on all of them. Okay, I am one of the first people to tell you this is a great idea, but each of these propositional variables represent single items. I want to generalize. What do I talk when I want to talk about multiple things going on or more than one thing being true at a time? I need to look at these sorts of things. We're going to do a little more grammar discussion on Friday. I will see you all then. Have a wonderful rest of your day. You are reminded, chapter 2, section 2 is due that day.